Okay, welcome back everybody. So in this video, the goal is I want to follow up on our introduction to the ARM pipeline and show some examples, go through some practice problems, and I think going through these, it'll really start to sink in some more about what we're doing and be able to visualize what's happening inside the processor, right? I do personally find this topic and similar topics related to computer organization really interesting because what we're really doing is we're pulling like we're kind of going and opening up underneath the hood and looking at how's the hardware actually running the computer code that we've been learning how to write going back from the previous courses that you've taken. So you take some classes where you're looking at some digital logic, and you take some classes where you're doing some programming, and then what we're seeing here is how we start to bridge that gap and how they come together. And anyway, let's jump in here and let's take a look at what's going on in the ARM pipeline. Now, I want to, as part of kind of recapping this a little bit, I want to just trace through what's going on at the various clock cycles for running. Say we're running a bunch of, a program with a bunch of instructions. And I'm going to label each instruction I1, I2, I3, etc. for instruction 1, instruction 2, instruction 3. Okay? So here on your screen is we're looking at the pipeline and we're saying, well, at clock cycle 1, we have instruction 1 is in its first stage. Okay, instruction 1 is in the instruction fetch stage. And what we're going to see here is as we move along, right, pretty obvious thing happens. At each clock cycle, we're advancing everything one stage. Okay, so instruction 1 moves to the decode stage, clock cycle 3, instruction 1 is now in the execute stage. And notice we're filling the pipeline, right? Instruction 2 is in the decode right stage, and instruction 3 is in the first stage, the instruction fetch stage. Okay, clock cycle 4, right? Now clock cycle 5, we have the pipeline is filled. Okay, at clock cycle 5, we have 5 instructions in the pipeline, and now we're using all of the hardware resources available to us inside the computer processor. Okay. At that point, moving beyond clock cycle 5, when clock cycle 5 finishes, we've now completed the execution of instruction 1. So notice it takes 5 clock cycles to complete one instruction, okay? But however, because everything's running in parallel, right, once the pipeline's full, we're completing an instruction at every single clock cycle. Okay, so this would be at clock cycle 10, we've got instruction 10 has entered its instruction fetch stage and so on. Okay. All right. So, if we were going to ask kind of a fairly basic question, say, well, how many clock cycles does it take to complete 10 instructions? Okay. Well, for the most part, we're finishing one instruction per clock cycle, and then we just have this extra 4 clock cycles it took to kind of fill the pipeline. Okay. So to run 10 instructions, right, that would take 14 clock cycles. Okay, so how many clock cycles to complete 10 instructions? That would be 14. Okay, as you can see, the limit of this is as we're running large numbers of instructions is that we are able to finish an instruction at every clock cycle, ignoring any sort of delays or things that could happen and that would slow this up. All right, we're having kind of a little bit of oversimplified model here that we're looking at in this course. Okay. But for now, we're looking at it as each clock cycle we're completing one instruction. Okay. All right. So this is a more thorough example or a more detailed example where we look at visualizing the ARM pipeline implementation. Okay. And when we see these pipes, right, these bars that are coming down and dividing up the different stages of our pipeline. Okay. These are registers. These are registers that are storing information between clock cycles. Okay, so we are writing to these registers by the end of the clock cycle. Okay, and we are reading to them at the following clock cycle. Okay, this is allowing us to propagate data and be able to store the state of data as it proceeds from clock cycle to clock cycle. Okay, so information as it completes, say, the fetch stage, right? We're going to write that. That machine language instruction information is going to come in between stage 1 and stage 2. It's going to be stored in that instruction fetch, instruction decode pipe. Okay, we're doing this for all the information throughout the entire pipeline, right? So we can see even control signals, right? We're going to In the instruction decode stage, we determine the control signals for that instruction. Okay, and we are going to store those control signals that are going to be needed in subsequent stages. So you notice that we've got three different stages that are going to be happening after the decode stage. We're going to have some control signals for the execute stage, the memory stage, and the write back stage. Okay, we need to propagate those along as the instruction's processed. Okay, now obviously as we move through the different stages, right, when we're heading into the mem stage, we no longer need to have that execute data preserved because we've gone ahead and already used those control signals in a previous stage. Okay, that's why we have this kind of drop off in what we're storing related to control signals in blue as we move through each one of those stages. Okay. All right. You're going to look at this diagram, and this is what I was saying in the previous video about how important it is to have a firm understanding of the single cycle implementation, because this effectively is the same thing, except we're doing a bunch of stuff in parallel, right? So if you understand how it's propagating between the stages and the fact that we're having these shorter clock cycles that are timing things between the stages, and you combine that with the knowledge of how the single cycle implementation works, and then you're in very good shape to understand the ARM pipeline. Okay. All right. So let's look at this from the perspective of answering a few questions. So here, what we've got is we're going to assume that we have a bunch of instructions that are loaded into instruction memory here on the left. All right, we've got all these different instructions, and we're going to assume that they're all loaded into instruction memory at these different addresses. And if we're assuming that they're 32-bit instructions, they're going to be separated by four, the address by 4 each. I'm going to actually change this to indicate that's a 1, so that we have this nice smooth adding of 4 at each location. And what we're going to see here is we can say, okay, this is our we're going to assume this is our instruction memory on the left, okay? And then on the right, we're going to say, okay, this is our register file. This is our register file. We're going to assume this is the state of the registers at the onset of the program running, okay? So we need to know the state of some memory before we kind of answer some of these questions, right? Not necessarily this first question, some of it's not relevant, but we're going to have some follow-up questions here, and they're going to depend on the state of the system when the program starts running, okay? So the state of basically what the program is, it's already loaded into instruction memory, and then what is the state of the registers, what data is already in the registers when it starts to run, okay? We're going to assume that there's already some information stored in the register files, so we have some meaningful data to work with, okay? All right, so the first question says, how many clock cycles does it take to run this entire program, right? Pretty basic question, right? We're going to see something similar to what we just talked about a few minutes ago. Right, let's just count how many instructions we have. We've got instruction 1, instruction 2, 3, 4, 5, 6, 7, 8. Okay, so what we have for the number of clock cycles is we have 8 instructions, plus it takes 4 clock cycles to kind of fill the pipeline, right? So you think about this, right? It takes 5 clock cycles for 1 instruction to run, okay? Right, once we've done that, right, once we've run 1 instruction, then they're gonna happen all back to back, right? Okay, so we've got, in this case, it's nice and simple, 12 clock cycles. Okay, now the reason we care about a question like this is it's just kind of getting an understanding of how things are happening in parallel, how things are timed. Okay, let's take this a little bit of a step further and say, well, what clock cycle does the first store instruction enter the decode stage? So let's break this down a little bit. Let's first look at the store instruction as our 4th instruction, okay? And the decode stage is stage 2, okay? Stage 2. All right. So the answer to this is going to be clock cycle 5. Right? It's going to be clock cycle 5, and the reason Okay, the reason for that is this instruction is going to enter the fetch stage at clock cycle 4 because it's the fourth instruction, right? But then it needs one more clock cycle to get to the second stage. Okay. All right. Let's keep going with this. Say very kind of similar question in a way. We've got the ADDI instruction, the add immediate. When does it enter its execute state? We're going to have a similar kind of way of approaching this problem. We're going to say, okay, we got instruction 1, instruction 2, 3, 4, 5. So this is instruction 6. Okay. And the execute stage is stage 3. Okay, stage 3. So the answer is going to be our 6 plus 3. Right? So we're going to say it's clock cycle 9. Okay? Right? Because it enters at clock cycle 6. I'm sorry. It's actually going to be clock cycle 8, right? Because just like how here, stage 2, it's just one more, right? Stage 3, it's actually, okay, if we look at this, right, at clock cycle 6, we enter the instruction fetch stage, right? And then we're going to go to decode, execute, 2 more clock cycles. So the answer is actually clock cycle 8, okay? Clock cycle 8. So that would put the add immediate into the execute stage, stage 3. Okay. Let's look at this a little bit more of a detailed way. Okay, let's look at a more detailed example here that's going to require a bit more tracing to figure out the answer. And let's say that we want to figure out some specific locations that are in the pipeline data path at a particular instance in time. So this instance of time, let's assume clock cycle 7. Let's say at clock cycle 7, let's figure out what some values are of some specific locations, okay, that are going to be labeled A, B, C, D, and E. Okay, these locations I could see here on the diagram, right? That we've got location A is the program counter. Okay, B is the value read from register 1. Okay, and notice each one of these letters is intentionally selected as something that's in each of the 5 stages. Okay, C is the input, the second operand that's input into the ALU. D is the address into memory, or if it's bypassing memory, okay, and going to the write back stage. Okay, and E is the value written back to a register. Okay. All right. Let's break it out one step at a time. So just to kind of recap here, we're trying to figure out those values in the pipeline data path at a particular instance in time, okay, at clock cycle 7. So one of the first steps of answering this is just to figure out what stage, right, basically at clock cycle 7, which instruction is in stage 1, stage 2, stage 3, stage 4, stage 5. Okay. Let's go ahead and do that. All right. We've got our instruction 1, 2, 3, okay, 4, 5, 6, and 7. Okay, and we know that at clock cycle 7, instruction 7 is just starting. It's in stage 1, instruction fetch. Then we're kind of working, in a sense, we're kind of working back up, right? Because instruction 6 is further along. It's in the stage 2, right? Instruction 5 is in the execute. Instruction 4 is in the mem stage, and instruction 5 is in the write back stage. Okay. And if I made this example appropriately, which I think I did, there was no weird issues going on where we don't have any real dependencies or anything where we're writing to a register and then reading that value later. I don't think we have any of that in here that's going to impact us. So I think we're good. I'm just kind of scanning it, looking, double checking. So we don't have to kind of look at tracing all sorts of weird things based on things getting updated in the program at an earlier date. Okay. All right, so now we know that each of these instructions are at these various stages during the, at clock cycle 7, this is at what's at each stage. So now we could start kind of answering these questions. So let's just take it one step at a time. Let's look at location A. Location A is the value of the program counter at clock cycle 7, okay? And we know that that value, okay, must be the current, it must be the current address, okay, that's being read into the instruction memory. Okay, so A, this is going to be our A right here. A is going to be value. Okay. At the decode stage, we have instruction 6. So let's look at location B. And location B is the value that is read from read register 1. Okay, the value that's read from read register 1. If we look at that, okay, the first register read here, okay, is going to be this here, R7. Okay, and R7 has this value. Okay, so location B is going to be 1110. Okay, I think that's 14. Okay. Okay. So let's keep going with this. If you kind of see the format that starts coming together here, we look at the execute stage. Let's look back at the processor diagram here, and we could see that at the execute stage, location C is the second operand into the ALU. Okay, so location C is the second operand into the ALU, and if we go ahead and we look at that, we notice that in the context of a load instruction, right? A load instruction, what's going to be processed there is, remember, the ALU takes the base address plus the offset. Okay, in this case the offset's actually 0, right? The offset's 0, right? We kind of come back to the diagram here. We can actually see that in the diagram, right? If you kind of recall that the processor for a I-type instruction is going to follow this path here, right? It's going to take the immediate field through the sign extender, right? And we're going to have the ALU source control signal sending a 1 to select that value. Okay, so that's the offset value. The offset value. So we know that location C is going to be 0 for the offset. Okay, continuing working back up, when we look at the MEM stage, that's location D in our diagram. Okay, and D is the address that's going into data memory. Okay, so the address going into our data memory here, and the address is, just like we just saw before, it's the base address plus the offset. Okay, is going to be that address. The base address plus the offset. Okay, so that in this case, because the offset is still 0, it's just whatever the it's really just whatever the base address was. So in this case, it's the stack pointer. Okay, we've got that value defined here. Okay, so that is going to be our value of 1 followed by 4 zeros. Okay. All right, and then the very last one, we're looking at the write back stage, location E. If you look at location E in our diagram, we see that that is the data being written back to the register file. Okay, the data written back to the register file. And if we look at the instruction here that is running in the write back stage, it's R5 plus R5 is what's going to be written back to the register, right? R5 plus R5. Okay. R5 plus R5, so R5 is 1100. Okay, so we've got our, you can just kind of quickly do that out. We got our 1100, 1100, right? Oops. Okay, so that we have that as our value that we're going to be writing. Okay, and that's our answer to this problem. Right? If you understand how I got all those numbers, right, I think it's a very, very good thing to practice because it really forces you to understand how things are timed, what's in what location at a given clock cycle, understand how to interpret these instructions and figure out what's going on. If you're able to do that, right, you should have a really good conceptual understanding of what is going on in the processor, right, to be able to have this level of parallelism. Okay. All right, let me stop the video there. I encourage you, right, I might have gone a little fast. I did that intentionally because I know that you're able to stop the video, go back, listen to it again, okay? So rather than go too slow, I'd rather go too fast knowing that you can watch this multiple times. So I encourage you to do that, right? That's by design, as well as ask questions, like always, all right? Hope you liked the video. Please let me know if you have any comments that you think are going to help improve it for down the road. And I look forward to speaking to you later in the week.